Good afternoon. I want to tell about the investigation of SAPO11 structure by the combination of solid-state 27 aluminum, 29 silicon, 31 phosphorus in mass spectroscopy, and DFT calculations. Nowadays, the microporous silicon phosphates are widely used as catalysts in N-paraffin isoisomerization, N-octane hydroisomerization, and so on. The silicon phosphates are obtained by the inclusion of the silicon atoms in the aluminum phosphate structures, and the variation of the silicon atoms inclusion mechanism in the aluminum phosphate structures directly influences on the chemical properties such as acidity, catalytic activity, ion exchange, and so on. So the purpose of this work is to investigate the temperature dependence of SAPO11 silicon centers formation by the combination of solid-state 27 aluminum, 29 silicon, 31 phosphorus in mass spectroscopy, and DFT calculations. The research objects was SAPO11, such as uncalcined SAPO11, and the calcined SAPO11 samples with different calcination temperature from 500 to 900 degrees. And the reagents used for the synthesis of SAPO11 was orthophosphoric oxide, baimide, silicon oxide, and the propylamine was used as a template. Hydrothermal synthesis was used for the obtained of SAPO11. And after that, the calcination was carried out at the various temperatures from 500 to 900 degrees. And modern solid-state in mass spectroscopy makes it possible to determine the local environment of the nuclei, which included the SAPO11 structure and the series of the series of 27 aluminum, 29 silicon, and 31 phosphorus mass in the mass spectra of SAPO11 was obtained. First of all, the series of the 31 phosphorus mass in the mass spectra of calcined SAPO11 was obtained. It should be noted that the 31 phosphorus mass and mass spectra of calcined SAPO11 were characterized by the superposition of at least two lines. The first line was about minus 24 ppm, which could be attributed to the tetrahedral coordinated phosphorus sites with OH group, with O group, and the second line was about minus 31 ppm, which could be attributed to the tetrahedral coordinated phosphorus sites. And after that, the series of 27 aluminum mass in the mass spectra of SAPO11 was obtained. It should be noted that aluminum is quadrupole nucleus, and the second order quadrupole interaction broadening made the analysis of 27 aluminum mass in the mass spectra much more difficult. And the additional techniques were used in this case for the analysis of NMR parameters for quadrupole nuclei. In this case, MCOMAS technique was used, which made it possible to determine the lines positions in the 27 aluminum mass in the mass spectrum. And it should be noted that the 27 aluminum mass spectrum of uncalcined SAPO11 was characterized by the line, which position was about 5 ppm. This line could be attributed to the pentacoordinated aluminum sites, which appeared as a result the one water molecule combination with the tetrahedral coordinated aluminum sites. And after that, the series of 27 aluminum mass in the mass spectra of calcined SAPO11 were characterized by the superposition of at least three lines. These lines could be attributed to the tetrahedral coordinated aluminum sites. And The comparison of 27 aluminum and 31 phosphorus mass and mass spectra allowed to establish that the formation of SAPO11 stable structure during temporal calcination, such as one structural phosphorus and aluminum tetrahedral, but the most informative method for the study of SAPO11 structure was 29 silicon mass in a mass spectroscopy. First of all, the series of 29 silicon mass in a mass spectra was obtained, and the 27 silicon mass 29 silicon mass in a mass spectrum of uncalcined SAPO11 was characterized by the superposition of at least 4 lines, and it should be noted that the number of lines appearing in the 29 silicon mass in the mass spectra increased for calcination, and you can see the assignment of lines in these slides. But there is a problem. There is line assignment problem because the characteristic regions of silicalimophosphates and limusilicates overlapped. So for detailed study of the SAPO11 structure of the SAPO11 silicon centers formation, DFT calculations were performed. First of all, DFT calculations of NMR parameters for ALPO11 were performed using periodic DFT calculations. And after that, DFT calculations of NMR parameters for SAPO11 structure were performed. It should be noted that 35 substitution variations were considered in ALPO11. Using the combination of the solid state NMR spectroscopy and DFT calculations, the correlation of experimental and theoretical data was made. For example, this line was about minus 94 ppm, which was characteristic of 2 of the silicon associate atoms, and this one isolated silicon centers. And for example, this line was about minus 190 ppm, which was characteristic of 1 of the silicon associate atoms only. And it should be noted that, for example, the uncalcined SAPO11 maybe contain 3 isolated silicon centers and 1 silicon associate centers, and the calcination of suppose 11 maybe contain 4 isolated silicon centers and 1 silicon associate, it should be noted that the distribution of the silicon in the SAPO11 structure was characterized as isolated centers with the most probable structure, with the most probable location of silicon with O group directed into the big cavity of the ring, and using the combination of the solid state NMR spectroscopy and DFT calculations, it should be noted that the formation of silicon associates also took place even at only 1% of silicon, and associates could contain up to 5 silicon atoms. And in conclusion, 27 aluminum and 31 phosphorus mass and mass spectra illustrated the formation of the ALPO11 structure during calcination at 500 degrees, and the ALPO11 structures was characterized by the presence of 2 types tetrahedral coordinated phosphorus sites and 3 types of tetrahedral coordinated aluminum sites. And it should be noted that this structure was stable up to 900 degrees, and the incorporation of only 1% silicon in the ALPO11 structure practically didn't affect on the 27 aluminum and 31 phosphorus mass and mass spectra, while the 29 silicon mass and mass spectra were the most informative in this case. And according to the to the 29 silicon mass in mass spectra, the incorporation of only 1% silicon into the alpha-11 structure led to the formation of both isolated and associated silicon sites, and using the combination of the 29 silicon in the mass spectroscopy and DFT calculations could be made that the distribution of silicon in the alpha-11 structure was characterized as isolated sites with the most probable location of silicon with O group directed in the big cavity of the ring, and the formation of silicon associates also took place even at 1% of silicon, and associates could contain up to 5 silicon atoms. Thank you for your attention.
Thank you very much for your presentation. And please, questions.
May I ask a question? You have very broad spectra in all nuclei, and what is the reason? It's probably some disorder in the structure. And can you predict the width of the line from DFT calculations, and explain the reason why the lines are so broad? It's probably the bond angle distribution or something like that.
Okay, the lines of broad because first of all, you tell about the 27 aluminum mass in mass spectra, yes?
About phosphorus and silicon too.
Mm-hmm. The lines was broadened because, for example, the structures was different different defects, for example, and maybe the structure contained some water in the structure, and this allowed to the line of in the spectrum.
So this is dipolar broadening, but you apply magic angle spinning, which should remove everything. But I think that the source of the broad lines is the distribution of chemical shifts, and probably it is due to the different angles formed with oxygen, for example.
I think,
instructions. And can you predict this from DFT calculations?
The distribution of the silicon in the structure. Please repeat your question.
Distribution of the line width is probably due to the distribution of the angles in some tetrahedra and so on. The angles which are formed between silicon atoms, for example, and oxygen, so distort tetrahedra and so on.
The distribution of the silicon atoms influence on the chemical shifts, and for example, if we have isolated silicon centers, we have the chemical shift from, for example, 90, for example, minus 87 ppm to, for example, 100 ppm. And if we have the for example, the silicon associated atoms, the chemical properties is increased. For example, chemical properties for associated atoms maybe started from minus 100 ppm to minus 100 about 18 ppm.
Okay, thank you very much. Maybe
you.
you will continue discussion privately, okay? So thank you very much for your